Hello, my name is Tom Hutchinson. I am a retired metallurgist with a track record of research and development in metals and ceramics with published research papers and patents awarded. My last patent, awarded 20 years ago, covered the rapid solidification of aluminum solutions using magnesium oxide as catalyst, and my more recent work using aluminum phosphate solution and magnesium oxide is especially pertinent in view of the recent problems in Japan. The lab-scale tests which follow show the phenomenon, ending with the quite spectacular high-temperature firing of the freshly poured cements. When problems arise in nuclear power plants, nuclear radiation becomes of immediate concern, especially when the reactor itself or the spent rod fuel storage area is involved. It is important to protect workers from radiation so that they can tackle the problem and the public at large from fallout. There is probable application here for a high-speed setting cement/concrete based on aluminum phosphate solutions using magnesium oxide as catalyst. This combination can be controlled to give setup times in a few minutes or longer if needed, depending on the mixing and pouring equipment used. The cement will stand up to temperatures over 3000, making it especially useful when high temperature containment is also desired, as in the present Japanese nuclear plant crisis. The aluminum phosphate solution can also be premixed with boric acid before adding the catalyst, with little reduction in setup time. Boron has a high absorption of neutron radiation. A few minutes after initial setup, the cement can be hit with an oxypropane or oxyacetylene flame without exploding or cracking as conventional concrete would. Small amounts of fillers, such as fire clay or fly ash, can be added to improve suspension of the magnesium oxide prior to solidification. I am now going to demonstrate on a lab scale the phenomenon of using aluminum phosphate and magnesium oxide to create a fast solidifying, high temperature resistant cement/concrete. I'm now mixing the aluminum phosphate solution first, the aluminum phosphate solution, (15 mils or 20 grams). And now we're going to mix in the magnesium oxide catalyst, which I have pre-weighed to make things move along. And we add the catalyst, and then we stir it in, and in a few minutes it will solidify. I'm also going to add a small amount of a clay, to improve the suspension. This will improve the suspension during mixing and will actually contribute to the strength of the solidified slurry, or the solidified cement. One of the beneficial things that happens is that, here we are. A minute before solidifying, the slurry becomes very low in viscosity, enabling additional beneficial materials to be added. Now, the other important thing to be demonstrated here is that the use of boron, which improves the radiation absorption capability of the mixture, does not impede the solidification process, and we will now demonstrate that using the same 15 milligrams, 20 milligrams of the boron doped solution. This is the same as the first, except for the boron doping. Now we're adding the catalyst pre-mixed with a bit of the clay. And this is happening in real time, so you can see that we're talking about the first solution slurry has solidified and is very firm. And that we're talking about at the order of 3 to 4 minutes that happened. And now we're doing the same thing again, but with the boron doped aggregate. There it is. And once again it becomes very fluid just prior to starting the solidification process. Of course, we can go to slower times by using different grades of magnesium oxide. Everything depends upon the equipment that's to be used and the urgency of fast solidification times. So there is more than one control point to make the magnesium oxide aluminum phosphate slurry behave the way we want it to meet the particular circumstances. It is now very fluid, so other solid materials can be added if desired before the slurry is poured. I'm going to pour it now, and while that is solidifying, I'm going to demonstrate the other remarkable property of this magnesium aluminum phosphate mix. I'm going to show that we can take this solidified sample that we just poured and hit it with a very high temperature flame. As you can see, we have a solid cement-like sample, and now we're going to hit it with an oxyacetylene flame, showing that it has amazing resistance to falling apart when very high temperature heat in excess of 4,000 is applied. You have to put it on pause now while I light the torch. So now I'm taking that sample which we just poured a few minutes ago, and I'm heating it with an oxyacetylene torch, and you'll see that to everyone's amazement, the material does not explode as concrete would, or even fly apart, doesn't even crack. We're heating it up, as you can see, to a very high temperature. And it was only poured, remember, about 3 or 4 minutes ago. That was the first sample, the non-boron one. We are now going to take the second sample we poured, which was dosed with boron, and we will see basically the same phenomenon. We're heating it up directly with the oxyacetylene flame, and it is holding together, not exploding or cracking. Now, if this is of interest to you, I hope you will contact me at Hyperon, spelled Hyperon, Hyperon99 at yahoo.com. Once again, that's Hyperon99 at yahoo.com.